Jitendra sir, Rashekar.
Yeah,
Sir, we'll start slowly, sir.
okay. Otherwise, we can wait or 1 or 2 minutes more.
No, people will join slowly.
Okay, no issue.
We will start, sir.
Mm-hmm.
Okay, sir. So let me formally invite you for a minute, 2 minutes. Then you can share your presentation and you can start, sir.
Okay, sir.
Okay, sir. So very good afternoon, one and all. This is Rashekar from Geetham School of Technology. Today we have Dr. Jitendra Kumar Katiyar sir with us. So I would like to extend a warm welcome to Professor Jitendra Kumar Katiyar to this 5-day faculty development program sponsored by AICT Atal Academy. So we welcome you to this program, sir, Jitendra sir. So let me brief you about the professor, what is his research interest and professional experience includes. Dr. Jitendra Kumar is going to present on a topic titled Influence of Hybrid Nanoparticles, Particle Additives on Tribological Properties of Lubricant in Turning Operation. So presently, Dr. Jitendra Kumar Katiyar sir is working with Mechanical Engineering Department, SRM Institute of Science and Technology, Cotton Kultur, Chennai. His research interests include tribology of carbon materials, polymer composites, self-lubricating polymers, lubrication tribology, modern manufacturing techniques and coatings for advanced technologies. He obtained his bachelor degree from UPTU Lucknow with honors in 2007. He obtained his master's from the Indian Institute of Technology, Kanpur in the year 2010, and he obtained his PhD from the same institution in the year 2017. He is a lifetime member of Tribology Society of India, Malaysian Society of Tribology, Institute of Engineers, India, and the Indian Society for Technical Education, shortly called as ISTE, etc. He has authored more than 60 plus articles in journals as well as international and national conferences. He authored 2 books such as Automotive Tribology and Tribology in Materials and Applications in Springer and Engineering Thermodynamics for UG level in Khanna publications. Dr. Katiyar is active reviewer in various reputed journals such as Tribology International, Ware, Polymers, Defense Technology, Collides and Interface Communications, Journal of Materials Research and Technology, Materials Research Express, SN Applied Sciences, Engineering Research Express, International Journal of Surface Science and Engineering, Friction, Journal of Engineering Tribology, etc. He has also a guest editor for special issue in Tribology Materials, Surface and Interfaces, Lubrication Science, Journal of Engineering Tribology, Part J, Arabian Journal for Science and Engineering, Industrial Lubrication Tribology. Dr. Katiyar has also delivered more than 25 plus invited talks on the various research fields related to the tribology, composite materials, surface engineering, and machining. He has received a research grant from various government reputed organizations such as MHRD and SERB. So today we are very lucky to have a professor who has got expertise in this tribology. Very happy to have you here on this platform, sir. So we are looking forward to receive your knowledge that you have vast in this area of tribology of various applications. Thank you very much, sir, for being with us. So now I would like to request Dr. Katiyar to just to take the session and he may share the presentation. Thank you, sir. Katiyar, sir.
Yeah, thank you, Rashekar ji. It is very indeed to this introduction, and I am happy at least you introduced me in that such a wonderful manner. Before going my presentation, I just thanks to my director, Geetham Institute, HOD, Head of Department of Mechanical Engineering, Geetham Institute, and their colleagues who at least give me a chance to share my knowledge in this 5 days FDP program, which is sponsored by AICT and Atal Academy. So it is a very honored me, and it is for me that is a very honor, so that I can at least again a chance, because there's one time I also share my thought in some different topic. So I hope in this FDP program also maybe few attendees also attend my talk previously also, maybe. So that's why I always, my thinking is to deliver you something new, so that you never found that some repeatability of my talk in everywhere. So I have seen that a few attendees who attended earlier also in several platforms like GIA, MT, and this Kottayam, Kerala, Signite also. So that's why I choose the topic totally different here again. And in this area also, the lot of the research scope is there. So just I share my screen and then we'll start. I hope everyone is
Yes, sir. It is visible, sir.
okay.
Good, sir.
Just I'm moving. So I hope, sir, it is visual.
Sir, it is clear, sir. You may please go.
Okay.
Yes.
So today, just I again thanks to Dr. Rasekar, my friend there in Geetham, Dr. Ashok Jayachandran, who always encourage me and other things, and we collaboratively do some work in near future also. So this is the wonderful platform given by the AICTE at Academia to share the knowledge, and most of the attendees maybe learn something new things, and also they can learn and grab the something so that they can also imply these research thoughts in their master's or post doctoral degree. And also if some faculty members, they can also look into the future aspects of these things, and they can also try to publish some good research work in that particular area. So this is also an area where nowadays research is going on. This is called a nano cutting fluid. So nowadays single particle additives is most probably not so many used nowadays, not more used, but hybrid nanoparticles additives is used in a cutting fluid. Like we just add a 2 nanoparticle in that particular cutting fluid, and then we just perform that turning operation. And also nowadays this flood cooling and other things is totally eliminated because of the some environmental issues. So this is also well suited title for this green technology and sustainability aspects of that particular FDP theme. So in that particular course, maybe at last I will also show you some future scope in this particular area. So this is my contact number and my mail ID. If you want further any communication, then I am very happy to help you in that particular regard. So in this particular section, I just go from the very basics of that particular machining. Then we will move for from these basic aspects in that particular machining, then metal cutting, what parameter, then why we need to analyze the forces. So that we all these 5 points, these are the very basics. If you understand these things, then only you can go for the research, then it is useful. Why you need to analyze that particular forces, why you want to improve that, why you add that particular nanoparticle in that cutting fluid. So there are several questions arises, why only choose that particular cutting fluid. So first we'll move to the very basics so that you can go through it, relax it, because that is a lunch. After lunch time, it is always laziness will come, and because of the taking food, and immediately you are seeing here. I am seeing you in that particular platform. That is also amazing. There's total 44 participants still in there here in this platform. That is amazing after the lunch, and so that you just go through it, and then at last we discuss 2 case studies. Whatever I till now I did it, and further I am doing it. I am also proposing at last the future scope, and then I finally concluded my talk. So these are the outlines of my today's presentation. So most probably thing is, what is the metal cutting? So it is a very interesting thing is this machining. We just remove the material from any object. So it is kind of the family of shaping operation. So we just remove the excess material from any object in cylindrical rod or in block, and to obtain the desired geometry. That's why that is known as a material removal process. And this metal cutting or machining is the most important manufacturing process among all process. So almost all the product we just get the final shape and size by material removal, either by the directly or indirectly way. Directly means your tool and workpiece contact is there. Indirectly means your tool and workpiece is not in contact, but some other mechanism can remove the material, like unconventional machining process or non-traditional machining process like electric discharge machining, ECM, AJM, AWJM. There are several other processes through which you can remove the material indirectly. Your tool and workpiece is not in contact. So material removal processes basically divide into 2 groups, traditional and advanced. In traditional, we are not going into the particular advanced processes. We just go in the traditional process. So further traditional into subdivided into the cutting and finishing. So in cutting also 2 types of the things, either your object is circular shape or object is non-circular. If object is circular, then turning, drilling, boring, these are the kinds of the things happen. These are the operations you can perform. If there is non-circular, then milling, planing, shaping, gear cutting, broaching. These are the processes you just perform. In finishing operation, like either you are using the loose abrasives or bonded abrasives, these are the finishing operation. So material removal rate nothing but the relative motion between the workpiece and your cutting edge. Whatever the tool you have using, that cutting tool cutting edge with workpiece, the relative motion, the metal cutting occurs. So there are 2 types of the tool basically we use in that particular machining, either single point cutting tool and multi-point cutting tool. So important point in cutting is it can improve the dimensional accuracy and tolerances, whatever the desired shape and size. We can also achieve the internal and external feature, whatever you want to produce it. Drawback is due to that particular removal of the material, these things we just lost the material in the form of chip, and how we can decompose those chip, that is also very uh, important. These are the waste material. So mostly waste material happen in the machining, and most expensive of all the manufacturing processes, because here we use the cutting force, cutting fluid and some other parameter. So most of that's why it is most expensive process from the other processes. So there are 2 types of the cutting. I hope everybody knows that orthogonal cutting and oblique cutting. Whatever the operations we performed in actual lathe machine, all that cutting is basically the 3D cutting operation. So that is an oblique cutting operation. So if we perform turning, then milling, actual machining, then all are oblique cutting operations. So, but the analysis of oblique cutting forces is little bit tough rather than the orthogonal cutting. So what we will do in a study, we just analyze the forces from the orthogonal cutting in 2D. So XY plane, we just analyze it. But in oblique cutting, feed along the feed is also that force. We just analyze that particular oblique cutting. So this oblique cutting, we just analyze 3 forces: Fx, Fy, and Fz. So metal cutting conditions, like what is the workpiece material you are using, what is the material of the cutting tool, and what type of the geometry. So either what is the rake angle, back rake angle is most important thing. So this angle is very important in that particular turning operation. and cutting speed. So in cutting speed, feed rate and depth of cut, these are the, and then cutting fluid. So these are the principal cutting condition which is widely affect that particular one. So cutting speed is not that much affect in the responses of that particular turning, but feed rate and depth of cut and what type of the cutting fluid we are using, these are the most important cutting conditions in metal cutting. So we just take care of these conditions, then we will get the better surface finish, and also we will get the less forces at the interface between tool and workpiece. So that analysis we will do in that particular metal cutting. So major question comes in our mind, why we need the study of forces in machining. So these are the few things why we need to study those forces. So we can design the tool according to those force analysis, because what we will do, we just consider the tool as a fixed cantilever. This is like a tool. Sorry, this design is not. So this is cutting tool, and here your forces is applied. Then this is looks like this is FZ. Then it looks like a fixed cantilever with the point load. And then what is the deflection in that particular one? So deflection of beam and then bending equation M upon I is equal to sigma upon Y. We just apply it and we just calculate these stresses. So moment of inertia we know, I know, we can calculate this sigma. So due to that particular one, this sigma is nothing but force upon area. So this force we know, so this force we can calculate it by this thing. So if we know the forces, then we can calculate and design our tool. So in this way, we just design the tool for strength and toughness. Another thing, we just design for machine tool also by analyzing of those forces. And then if we know the forces, then we can calculate the power. So power is we can calculate by FC into VC. So cutting force into cutting velocity plus your other forces, but most predominantly this force. So these are the few things which is required to analyze by analysis of the forces. So that's why the force analysis in metal cutting is very important. So these are the three zones in that particular orthogonal cutting. So one is called this tool chip interface, then your this workpiece and tool interface. This is called a shear plane. So this is called a shear zone. This is chip tool interface zone, and this cutting forces, which is act by the tool over the tip of that particular workpiece. So these are the forces acting on that particular different zones. So here chip moves over the tool due to the friction happens. So chip is moving like this. Sorry, chip is moving here in this direction. Chip is moving like this direction, so friction force is always acting in opposite direction. So normal to that, your normal reaction. So these are one zone, and this is called your primary zone. That is a shear zone. This is your secondary zone, and this is your tertiary zone. So there are three zones. So shear zones, chip tool interface, primary, force on the cutting tool. So these are the few three zones where the forces act on that particular cutting. How we can calculate this force? We just use the force dynamometer. So basic function of this force dynamometer, you can see this image. So this image, this is the force dynamometer, and you just hold your tool post over that particular one, and this is the single point cutting tool. So when forces applied, when turning happened, this force applied over this tip, and due to that particular application of forces, so this force dynamometer consists these piezoelectric sensors. So X, Y, Z. So according to the deflection on this particular tip in X, Y, Z, these piezoelectric sense that particular deflection and sends to that software, whatever we are using, in a millivolt or in voltage. So that piezoelectric gives you that particular in a, whatever reading in a voltage form, but whatever ultimately you will get it, that multiplied by all the things, and then you will get in a Newton. So that whatever this piezoelectric sensor, this work on that particular principle of EMF and then generated, and your voltage is generated due to the application of forces on the tip, and these forces is taken care by these three piezoelectric sensors in that particular force dynamometer. So in this way, we just calculate the Fx, Fy, and Fz, and this x-axis gives you the Fx force, and this Fz and Fy. So these are the basic things in that particular one. So for calculation of the forces, we just know that particular one theory that is called a merchant theory. So that is these are the assumptions which are taken by the merchant in 1940. So Ernest Merchant in 1940, he just established those relations in the force, and this is that particular. They just make a merchant circle diagram. So sometimes question comes why they only select that merchant circle, only circle in to represent the forces. Why not others? So this question always asked in that particular classes also and something. So this is because your all the forces are perpendicular. So Fx is perpendicular to Fn, Ft is perpendicular to Fc, N is perpendicular to the F, that is a frictional force. So all forces are perpendicular. Then how you can represent the forces as perpendicular when their resultant pass through the diameter. So that is the theorem whatever we have studied in the 9. So when our this hypotenuse passes through that particular diameter, then whatever the angle made on the periphery, that is a 90 degree. That is the theorem whatever we have read it. So that's why diameter through the center of the circle, the R is resultant is passes, and all the forces are represents on the periphery. So that's why he selected the circle to represent the forces, and due to that particular one, they just calculate the uh, forces Fn, Fs, F, and N in respect of that particular Fc and Ft, and phi we know the shear angle, and alpha we know that backrake angle. After that, two models is also whoever work on the simulation, then they just consider for the two models shear zone model, that is known as the shear zone model. So basically, idealized model that is orthogonal. So 2D cutting with the well-defined shear plane, and that is called also called a merchant model. So in because merchant is considered that this plane, that is a line, a very thin line. So, but sometimes what we observe that this is not a very thin line, that is a thick zone. So that's why thick zone is also considered for the simulation purpose. So we just consider this very thick zone not in a line. But what is the problem in thick zone? It is only valid for a very low speed with high depth of cut and feed. But if your high speed, low depth of cut, low feed, then you always valid the thin zone model. So according to our velocity, feed, and depth of cut, these are the three important parameters. We just select which type of the model we are going to work, and according to that, we just simulate it in 3D deform software. So now we move to that particular little bit how this chip tool tribology comes into the picture, why this tribological analysis happen in that particular chip tool interface. So in first time in 1970s, chip tool interface interaction is studied, and in that particular study, the scientists what they just select that sapphire. So they just use the sapphire cutting tool, which is transparent in nature, and they just make a chip formation by this sapphire cutting tool. So they just observe the two zones, and they just mark that particular two zones over that in chip tool interface. So zone 1 is called sticking zone. So chip material is stick to the rake face because of the high temperature when it can detach from the shear plane, it is having a very high temperature. Due to that particular high temperature, and this cold welding happened in that chip tool interface, and that's why it is called a sticking zone. But after some time, immediately what happened, this sticking is changed to the sliding. So due to that particular change in the sticking to the sliding zone, some material is removed from the tool surface, because your now what is happening, your material is cold welded over the surface. Now if you want to move that material over that same surface, then some material can be detached from that particular surface. So that's why the crater wear, whatever you have seen on the rake surface, that is because of that reason it can means happen away from the tool tip, but the temperature at the tip is very high. So not happen in this, but it is happen little bit here, somewhat at the end of the sticking zone and the start of the sliding zone. So this is the reason why the crater wear happened little bit away from that tool tip. So when we analyze that particular surface, this from that thermograph, that IR camera. So here you can see this is the cutting tool, and we just perform a turning operation. And there is the primary shear zone. This is kind of that particular one, and this is the chip tool interaction. And in that particular chip tool interaction, you can see here the your crater wear happened a little away from that particular tool tip, and it is most probably at the end of that sticking, and this end and this sliding start. So these are the two zones. You can see that the sticking zone is little bit more rougher than the sliding zone. So that's why the tool tip, near the tool tip, it is very hot rather than the sliding tip. So these are the chip tool tribology happened after this, and then surface morphology also you can see here that because of this crater wear, the surface roughness is very high in the sticking region, and in sliding region the surface roughness is very low as comparison to the sticking region. So this phenomena, why this is happened, they just uh, Noru and Noru Jaffard, they just estimated the possible mechanism why it is happened. So they just estimated by this schematic what happened in the sliding zone, what happened in the sticking zone. So because every material has its own asperities. So in sliding zone, tool asperities and the workpiece asperities comes into the close contact. So though no asperities contact is there. So immediately, but when it changes to that particular asperities, move over the asperities, that is a sliding happen. Then this material can be, due to the cold welding, these asperities can be come out with that top chip. So that's why this crater wear happened in that particular sticking zone, at the end of the sticking zone and the start of the sliding zone. So this is the possible mechanism which is given by that particular in 2014 International Journal of Machine Tool and Manufacture. So this is the surface morphology, how looks like in that particular range. So we need to develop some cutting fluid to reduce these type of the things. We can at least reduce the frictional forces at the interface of tool and chip. So that is very, very important. So cutting fluid plays a very important role in that particular one. It can reduce that particular frictional forces, reduce the other forces also, shear forces and normal to the shear forces. So nowadays, basically, we just use that flood cooling. So this flood cooling is not that much appreciable because the sustainability aspects of the lubricant, how we dispose that particular lubricant in manufacturing industry. So what is the basic purpose of that cutting fluid is it can remove the heat at through interface at the interface. It can easily removal of the chip. It can also reduce the tool wear so that your tool life can be improved. and also you will get a better surface finish by using the cutting fluid. So these are the basic purposes of the cutting fluid. And this tool life we can calculate it by the Taylor's tool life principle, and further they just modified the Taylor type tool life equation by including of feed and depth of cut with the sum exponent. So wet cost of that particular wet cutting is like in tool changing 20 we just 25% cost in that particular manufacturing goes to the tool change. Sometimes your downtime machine is not working 7%, coolant 16%, tool 3%, machining 30%. So these are the typical end user manufacturing cost in that particular wet machining. So major problem in that particular conventional process or flood cooling is it can creates the dirt. It can also creates a corrosion and contamination of lubricating system, and also needs to storage. Additional floor space is required. Pumping system is required. Disposal system is required. Recycling system is required, and also it can pollute the environment, and sometimes it is also very hazardous for the health. Whoever is standing in front of that particular machine, the whatever the fume comes out at the time of machining, it can create the cancer, lung cancer or skin cancer, whatever the these are the two major cancers which can happen in that particular one. So that's why this flood cooling is slowly it is avoiding by the industry also. So now this is just, I just want to show you that particular image. So according to that particular temperature, whatever we want to machine it, and what type of the material we want to machine it, according to that, we just select the tool material, because that is also plays a very important role in machining operation, in increase the tool life and also improve the surface finish and reduce the forces. The tool material is very important also. But the most important parameter is cutting velocity, cutting speed, feed, and depth of cut. So nowadays, to avoid that particular drawbacks in the flood cooling or conventional method, we just use that particular MQL machining. So that is called a minimum quality lubrication. So here, as the term is represents minimum quantity. So this in this process, we just use the small quantity of lubrication, and which can force high pressure of the nozzle. It can just apply on that interface of tool chip interface here. So how they can go here? So we just have that particular setup. In that we just fill the cutting fluid, and then one side air will come. So compressed air. So one is the mixing, before the mixing chamber, this air and your lubricant can mix, and that comes out from the nozzle with a very high pressure. So normal consumption of the lubricant per hour, it is restricted to 10 ml to 100 ml per hour by using this MQL system. So it is very useful in the case of turning, milling, grinding also. So any machining process you want to use this minimum quality lubrication, it is very useful nowadays in a to make the environment green, less pollute, sustainable, and also reduction of the forces and improvement of the surface, increase the tool life. These MQL machining is widely used nowadays. So this is the just one picture I just want to show you. This published in Journal of Clean Production. They just shows that particular according to the feed. If we increase the feed rate, what happened in the cutting temperature in a various method. If you are working in a dry condition without any lubricant, if you are working in a wet condition, means you are working in a flood cooling or conventional condition, or MQL minimum quality lubrication. So by using this minimum quality lubrication, if you further increase the feed also, most probably you will get not too much difference in that particular temperature range, even though if you increase the feed also. So it is very less in that particular cutting zone. Why? Because we just means throw that particular mist coolant over the at the interface of the tool and chip. That's why the temperature at the interface, cutting temperature at the interface is less in case of the minimum quality lubrication. So these are the few basic things what I want to tell you. Now I just move to that particular case study, whatever we have did it here in that particular one. So both paper is published, and this first paper here I have studied in from the literature, and this is work done by my undergraduate student here. So they just mix the graphite and talc nanoparticle in that particular cutting fluid, that is a coconut oil. So why I choose this coconut oil? This edible oil is unsaturated and it is biodegradable, and graphite and talc is also biodegradable. So in that way, we can make the sustainable cutting fluid, which can easily degrade it, and also we can use the minimum quality lubrication method to increase the lubricants and increase the life of the tool, and also we can predict all the parameters, what are the basic component parameters which affects more in that particular responses, which is surface roughness and forces. So in this study, and also one more question I think in your mind, why I choose the graphite and talc? Because this talc is having the hydroxide group, OH group, and graphite is widely means reactive with the talc with the OH group, and then they can easily react, and then they bonded well in that particular one, this graphite and talc. And graphite property is it can provides the better things in the case of the lowering the friction, and talc properties, if you add the talc, so talc improves the wear resistance property. So I just use those properties and mix these two particles in that particular coconut oil with 50-50%. So in this study, I just formulated the 50-50% proportion of these two nanoparticle in coconut oil as a base fluid, and that I used in that particular minimum quality lubrication. So basic, I choose that titanium alloy grade 5 seat, which is widely used in the medical grade. Also, it is known as a medical grade, and the machining is not that much easy of titanium alloy with better surface finish and better tool life also. So what we will do, whatever particle we have mixed it, hybrid, I am telling here the hybrid nano cutting fluid that I have studied in the tribological behavior also in pin on disk machine, and we just parameters whatever we have obtained three levels, three parameters, three level. So we just make a Taguchi analysis, and then we perform the ANOVA and gray regression analysis for particular operating parameter, obtain the operating parameters, and also it can whatever the obtained parameters we also compare with that particular pure coconut oil in terms of the cutting forces and the surface roughness. So from this gray regression analysis, it is whatever we observe that feed rate has a larger influence on the responses as compared to the cutting speed and nanoparticle as well. So this is the machine which I used. This is the dynamometer, and this is the MQL setup. Here you have seen that, which is the 5 centimeter away from that particular tool chip interface, and this is the titanium rod, and we just perform that particular particular experiment over this setup. And this is the schematic diagram of that particular setup. So we have data acquisition software through which we can convert the obtained voltage from the piezoelectric sensors. It can convert and give it to you in a Newton. And this is the workpiece which holds between the headstock and tailstock, and this MQL pump. The air filter is there, which is connected with the compressor, and compressed air comes inside the pump, and we just fill that particular pump with the cutting fluid, and they just mix in that particular mixing chamber, and that mixed cutting fluid comes through that nozzle at the interface of this. So this is the basic schematic of that particular turning operation. So these are the variables which I have taken: the cutting speed, three variables, feed rate, depth of cut, and also varies the nanoparticle concentration. So four variables, three levels. So this 0.25 is nothing but 0.125% graphite and 0.125% talc. So this is the 50-50% concentration of the both nanoparticle in the coconut oil. So this is the response parameter, whatever Taguchi we have obtained it, and according to that we just calculate the forces, and also we just calculate the surface roughness by the portable surface roughness tester, and we obtain that particular 0.25 concentration and nanoparticle, and 0.1 and 0.1 feed rate, 0.1 depth of cut gives the better surface roughness and the lower cutting forces, which is our objective of this work. So through this analysis, we just perform this gray regression. We analyze the gray relation coefficient, then the gray regression rates we just analyze, and according to that we just rank it, and we found that particular seventh experiment, whatever this parameter, it gives the good result in terms of the cutting forces and surface roughness. So we just perform the we further gives the rank for those three levels according to that velocity, feed, depth of cut, nanoparticle concentration, and we just give the ranking, and according to that which gives you the particular more in terms of that in case of this optimum parameter, whatever the cutting forces and the surface roughness we have obtained. So this is the cutting speed, which is I think it is cut here. So first term is the cutting speed, feed, depth of cut, and nanoparticle concentration. So you have seen here the whatever the feed we have given to the tool to cut that particular machine, that contributed 50.55 means more or less 51%, then depth of cut, then cutting speed, and then nanoparticle concentration. These are the percentage contribution in surface output parameter, which is the cutting forces and the surface roughness. So through this we just analyze this, and minimum is so maximum to minimum we just go it. So we just see that 450 it is a better one, point feed 0.1, depth of cut 0.1 and 0.75. That is that particular nanoparticle concentration. It is good for particular further application. So what we'll do, we just optimize those parameters. So 450.1, 0.1, 0.75 concentration, we just calculate that particular cutting forces, and this is the term for the surface roughness. So cutting forces for nano cutting fluid and pure coconut oil, we just obtain this optimized data. And further, because this is the Taguchi method, because if this 4x3, that is most probably a T1 experiment. So I just select another term through manual way. Okay, we just perform 450.1.5. This is the confirmation test. Either that is whatever the optimized data we have obtained, either this confirmation test we have performed it, and we just observe that the variation in that particular optimized data and confirmation test is in between 1 to 5%, which is the permissible limit of acceptability. In case of surface roughness also, that varies is not that much, even though we increase the depth of cut 0.1 to 0.5. So we just percentage variation plot with the response parameter and obtain that the this cutting forces is 21.19% and 18.9% in the surface roughness. Variation with the pure coconut oil we observe in case of the hybrid nano cutting fluid. So cutting edges also we just see by the SEM micrograph, so scanning electron microscopy. So this here you can see that this is the flank wear happen on the edge of the cutting edge of the tool, and you can see the more flank wear. That's why the forces in that experiment 3. These forces in experiment 3, you can see this is the highest forces 414.658 Newton, and also surface roughness is more or less higher. So this you can see by these same images. It confirms that this experiment 7, which gives our lowest coefficient of lowest forces and also better surface finish here. No wear mark we obtained in that particular experimental 7, but in other cases at least somewhat minimum, or in some cases we obtained the maximum flank wear in that all the cutting edges. In the chip morphology also we observed that the more curly edges is found in experimental 3. You can see that particular plain chip, and this is the more thicker than other, and also it is more curly, so that's why the forces acts in that particular experiment 3. It is very high, and also it gives the higher surface roughness. In experimental 7 we just get the discontinuous type of the chip. So because we know that in the if we fabricate the discontinuous chip, then the cutting forces and we can also reduce the cutting forces and improve the surface roughness of the surface finish. So because of that reason, you can see here that this discontinuous chip, we can get that particular less forces and better surface finish. In optimized condition also the more or less discontinuous type of the chip, but still it is some curly, but that is a very, very thin thickness of this chip is very small, and it is most probably curly, but it is also a discontinuous type chip in optimized condition. So further what we will do from this analysis, we observe that this optimized data we obtain in lesser cutting forces and better surface finish. So we just need to check that particular cutting fluid, whatever 0.75% concentration nano cutting fluid, which gives the better results in terms of forces and surface finish. We just check for that particular one tribological study. So in that, for that particular cases, we just perform test that nano cutting fluid on this pin on disk setup. So here what we'll do, we just use the 0.75 concentration of cutting fluid, 1.25, all the cutting fluids, and we just observe the coefficient of friction with respect to time, and we observe that the almost probably is same, but in case of that particular 0.75% concentration, it gives the lowest coefficient of friction. So when we increase the concentration, obviously the more number of particle comes at the interface, it reduces the friction, but further increment in the concentration at the interface, agglomeration problem is happened. So because of that reason, you can see that here 1.25% concentration of hybrid nano cutting fluid increase further the coefficient of friction from the 0.75 concentration nano cutting fluid. Because of that reason, so agglomeration, concentration of particle more, so that is also acting, those particles also acts as some shearing action happen because of the rolling each other. So increase the friction between those particles also. So because of that reason, the friction coefficient increases, further increase the cutting fluid. So this also shows that this analysis, this 0.75 nano percentage concentration nano cutting fluid gives the better result. And wear analysis also shows the same thing. So we are in micron, we have observed, and then 0.75 gives the better result. But all the, after adding the hybrid nanoparticle in base fluid, the friction is always less than this, and that's why the wear is also less. But these things I have tested on the AISI 34 cylindrical pin, because titanium pin is very costly, and we don't have the money, and also no one will provide the 25 diameter, 25 height pin. So these are the easy available materials. So my objective was to only test the hybrid nano cutting fluid. So that's why we have chosen that AISI 304 cylindrical pin, and this is the particular EN31 plate. Over that, we perform this Tribological analysis. And after this analysis, we just check that particular sliding pin. What happened in that particular sliding pin, why this thing shows that particular one. So these are the pure coconut oil. You can see that the cluster and sliding scar is there, and some cluster formation has happened. So surface is very uneven. So that's why the coefficient of friction is higher and wear is also more. But in case of graphite and talc with 0.75 volume percentage during pin on disk driver test, you can see that the very smooth surface, pin surface. So that because of that reason, we are also observe in the case of friction is very less in case of the 0.75% concentration of the fluid. So what is the possible mechanism why this happened? Why lower that particular forces, why the surface roughness improve? So this is the possible mechanism which I propose in that particular one. So when we throw that particular flow, that mist lubricant at the tool chip interface at a very high speed and high pressure through the nozzle, so those nanoparticles come to the contact between the tool and chip interface, and because of that reason they just slide each other, and then this tool chip interface is not contact, and they just make a very thin tribofilm at the interface between tool and chip. Because of that reason, the forces act on that particular tool chip interface is less. So resultant force is less, even though it improves the surface finish because of that reason. So this is the possible mechanism which I have proposed in that particular paper. And this paper I have uploaded in Journal of Manufacturing Process JMP in elsewhere. So still it is in decision in process, it is showing in last 7-8 days. So I am waiting that particular decision from the journal editor. So this is the work. Another work, so conclusion from this work, whatever I have already shown, told you that in case of cutting forces, so we observed that if we use the nano cutting fluid rather than the pure coconut oil, a significant reduction in the force and surface roughness is respectively 22% and 19% respectively from the hybrid nano cutting fluid compared to the pure coconut oil. And 0.75 volume percentage of hybrid nano cutting fluid shows the better results, better output parameter. Just observe it like surface roughness and cutting forces. These are the few things. And also flank wear I have not measured, but flank wear also obviously I showed you that same image of the cutting edge. So flank wear also we can measure it, and then flank wear also reduced. So these are the only two wears happen on the tool, that crater wear and the flank wear. The flank wear happen on the flank face and the cutting edge, and crater wear happen on the right face because of this sliding or sticking and sliding phenomena. Another case, study I just, so this is the future scope. I think this I will discuss you at last. I just uh, keep this slide early. So another case study, this paper published in the Friction Journal, that is a Springer. So here we just mix the aluminum and multi-wall carbon nanotube nanoparticle in the water-based lubricant, and then we just perform the turning operation on aluminum alloy. And these are the TEM images of the mixed aluminum MWCNT uh, nanoparticle, and you can see that the aluminum mixed particle and MWCNT nano fluid and aluminum and MWCNT hybrid nano cutting fluid. So clearly we can observe that the mixing of that homogeneous mixing of aluminum and MWCNT nanoparticle inside the fluid. So here also we just take the cutting parameter, 3 levels, 4 parameters, velocity, feed, depth of cut, and nanoparticle concentration. So same 0.25, 0.5, 1.75, 1.25, and we just increase the speed 60, 90, 120. So that these are the 3 levels, and here I have used the RSM method that is also used in that optimization method. So in this RSM method, we just designed the 27 experiment, and we also calculated the temperature at the interface by K2 thermometer, and we just measure the flank wear in the micron. So for aluminum nanofluid or hybrid nanofluid or single nanofluid or hybrid nanofluid, we just observe that particular data. And in that particular data, we observed that 0.75, it gives the lowest one. There's 56 micron flank wear rather than other cases. So we just take care of the optimum data, and then from the this RSM method, we also obtain the sum of data. So in that particular data also, we just perform the test, and we measure that output parameter of temperature and flank wear for both cases of aluminum nano cutting fluid or alumina with MWCNT nano cutting fluid. So these are the optimum parameter whatever we have obtained by through the software. And this is these are the tool images which I have taken from the microscopy, and you can see that particular one. This is the aluminum one, and this is the nano hybrid one. And in this hybrid one, very low flank wear which is obtained in that particular one. Whatever the optimized parameter we can get from the software RSM method, that we have also tested, and we can see clearly that optimum very low flank wear in the cutting edge, very small wear happened rather than the other cases. So further, we also perform the Tribological test on same pin on disk machine, and these are the with the cutting forces coefficient of friction with respect to time, and we found that initially that whatever hybrid nano cutting fluid, this gives the higher friction, but after some time it is gives the lowest friction. This is higher because initially higher because the more particle comes at the contact, and after that they just act as a increase the lubricity, and they start decrease the coefficient of friction because of that reason. Here only single nanoparticles, so because of that particular one it start low, but this continuously also decreases, but more decrement observed in case of the nano cutting fluid. In case of wear scar also, we have seen that the less wear happen on the pin over the pin surface in hybrid nano cutting fluid as comparison to the single nano cutting fluid. So these things we have observed in that particular SEM images. So in SEM images also we have seen that the same phenomena. So for 0.25 volume percentage particle, we can see that both alumina and this hybrid. So better surface rather than the single particle. And for this optimum surface, you can see that the smoother surface obtained, no pits formation in that particular pin surface. So this shows that the whatever the optimum results we have get it, that is confirmed correct results in that particular case. So these are the few analysis done in that particular area. And this possible mechanism, I already told you that when hybrid cutting fluids come in that particular contact, then tribofilm formation happen. So this conclusion from this is we also tested that particular contact angle and the significant reduction of 27.36% nodal temperature, and flange wear is reduced by 11% in case of the hybrid nano cutting fluid. So mixing of MWCNT with alumina nano cutting fluid also enhance the thermal conductivity, that also we have tested by the portable thermal conductivity meter, and it can increases with increase of nanoparticle. So thermal conductivity of the fluid is also very important parameter in case of the cutting fluid. So this is so future work of these studies is I can say that you can basic further in analyze the influence of hybridization of various different nanoparticle with the 50-50 percentage or maybe 60-40, whatever you want. Still research scope is there, and you can further investigate this analysis for the various combination of the nanoparticle in different concentration also. You can also vary the volume fraction of nanoparticle and optimized those particular volume fractions, that is only corrected, and you can propose for that particular industry. And also this study can be very useful, may be very useful in developing the suitable nano cutting fluid for the super alloys like Highness 16, cobalt chromium based alloy, safe memories alloys, and metal based alloys also for specific purposes. And or further you can investigate for performance considering different shape, size and concentration of nanoparticle also. That is also very important. If your nanoparticle shape and size is different, then this analysis is also different. What is the effect of the shape and size of the nanoparticle is still you can do it. And also further you can optimize the parameter such as the flow rate of the MQL system, spray distancing, like I have kept 5 centimeter. What is the effect of the distance between the nozzle and the tool chip interface? That also you can optimize it. Angle of spray nozzles, different angle you can set it. Air pressure also you can set it. So these things also you can optimize it. So there are huge scope in this area of turning uh, research of hybrid nano cutting fluid by using the minimum quality lubrication for various material. Maybe you can use for you can choose the super alloys, you can choose even though aluminum alloys, and before choosing the material you just choose the application, which application you are targeting. That is very, very important. So thank you very much. This is from my side. So any questions from audience, I am happy to answer you.
Thank you, sir. Jitendra, sir, thank you very much. That was a very detailed and elaborated explanation that you have given with a lot of patience. You have started with the concept of machining and green components in machining fluids, nanofluids, characterizations, almost all you have covered, sir. And definitely, I feel like this would be of great help to our attendees. Most of them are like researchers and faculty members, and some are looking forward to start their research, and this could be a great source for them to give a kickstart to their research activities. That was very nice presentation, sir. Jitendra, sir. Thank you very much. Let's look for some questions, sir. We got one question in Q&A by Julie Charles. The question is, sir, what about the thermal stability of nanofluids? Are they stable at high temperatures?
So this MWCNT is always used for the high temperature thing. So when you select the nanoparticle, according to the temperature you just selected, like hexagonal boron nitride, you can also select the hexagonal boron nitride. So that is sustainable up to 1000 degrees centigrade. So whatever the nanoparticle you are selecting it, according to the application you selected. If you don't need that particular high temperature application, then don't go for that particular costlier nanoparticle like graphene, MWCNT, hexagonal boron nitride. They are all sustained up to 1000 or 1200 degrees centigrade. So according to that particular, alumina is not that much. Alumina is only up to 400 or 500 degrees centigrade. So according to the application, we can also choose the particular nanoparticle. So that is beauty in selection of the nanoparticle.
Yes, sir. Yes, sir. Very good, sir. That's a very good answer. Hope our attendee Julie Charles might have received the answer. And I request any participant still, if you have any doubts, you can just put it on a Q&A so that you can straight away get an opportunity to speak to the speaker and you can get your doubts clarified.
Otherwise, they can directly.
Yeah. That's of course.
You just unmute. If somebody
Yes,
raise
sir.
the hand, then you just unmute them.
Yeah.
And
There's also one more option. If people cannot come out with a doubts or something, you may get later. So you may just post those questions on our group. We would convey to forward those questions to Jitendra Kumar sir, and we will get back to you. So hope there were no questions from Q&A, sir, from the
I think
participant.
one person raised the hand. Victory.
Yes, sir. We have seen one person. There's some Purushottam, sir.
Purushottam sir, no, but this one person.
No, yeah, sir. Vitrivel, sir. Vitrivel, sir. Are you there, sir? I'll let you speak to the Jitendra, sir.
If any attendees wants to speak, then please speak. No issue.
Yeah, sir. And we also welcome such participants being active. Vitrivel, sir, are you there, sir?
On my side, only suggestion is if you want to achieve something in your life, do hard work.
Yes, sir.
No shortcut in life.
Yeah.
So even though in research, if you're sometimes you not able to find the good results, that is also not waste. That gives you some kinds of the learning. So don't frustrate by the bad results in your research. That is also good for you, good for others, so that you can also guide to some other candidate in such a way that no, this path is not correct. You just choose this path. So sometimes the bad results is also very good to learn. And
yes, sir.
learning process is by itself only. If you want to learn something, then you start from the somewhere and never stop it until and unless you will not achieve your goal. That is my suggestion. And try to always do and achieve whatever you set the goal. Set the goal not for very short, set the goal for the long. And don't take any shortcut in your life if you want to be a successful person in your life.
Yes, sir. That was very good. That was a very good motivation from Jitendra, sir. That's exactly correct. Like, of course, like we can find some people nowadays looking always forward to have things are getting done in a shortcut manner, but that definitely won't yield a very good thing. So hardworking would definitely yield a positive result. Of course, the basic definition of the research itself says like highlights. Every research may not yield a positive result, but sometimes it may also yield a negative also. But there plays a role like the way how you present the negative also in a favorable way would helps a lot. So that was very amazing, sir. Good motivation for the fresh researchers looking forward to kickstart their activities of research. Sir, hope like we don't have any more questions here. Like we still have that Vitruvels are rising hand, but maybe he's not available or some technical issue he may face.
Maybe.
Anyway, I'll request
No
participants one
issue.
more time.
I will again join any sessions and then I can answer any questions regarding this.
Yeah, yeah.
I always try to keep new things, new idea in every new lecture. So previously I presented on the brake material. I
Yes, sir.
thought that I just present now this because I only get the undergraduate students. So I
Yes,
just
yes.
work with the undergraduate student. I give the problem to undergraduate student in various area, and they just at least I found a few good student in who wants to do something in life. That is important. So nothing is the waste, even though coal is not also not waste. Even though if everybody likes the diamond, but I always likes the coal.
Exactly.
If you are the good goldsmith, then you know how to make these things in a presentable manner. That is very important.
Yes, sir.
If everybody likes the horse, then what about the donkey? Quality of the teacher or quality of that particular any person, any motivator is if you can make at least donkey to horse, then that is the quality. If already that is a horse, then what is the new thing you add? Nothing.
Exactly.
Means you always actually, but nowadays everybody wants the horse. Nobody wants to take the pain. But when you try to explain anything to the little bit not a much understanding person, if that person can achieve something in life, that gives the more satisfaction rather than who is always intelligent.
Yes, sir. Yes, exactly. So that was very good, sir. Like I've been saying, like
I hope I have finished on time.
yeah, we have finished. We have started exactly according to the schedule, and we have finished it. Like hope like all attendees like got very good stuff from Dr. Jitendra Singh Katiyar, and hope this would help a lot in finding their areas of nanofluids and
Hope
relevant
in near
tribology
future
applications.
also, sir, I will again interact the persons in this platform or whatever in physical mode also,
Yeah.
because in sometimes what happen physical mode is more better than whatever I feel that because at least we can give some expression and through expression also somebody understand.
Yes, sir. Exactly.
That is the thing. So okay, thank. This
Let
is my pleasure. You have given me a chance to again interact to the attendees by this AICT Tel Academia sponsors FDP.
It's
So
our pleasure that we got opportunity to have you as a resource person here, sir.
I always think that
And
start from the basics and go to the higher. Don't go again. Start from the higher, so nobody understand what is going on. So
yes,
that
yes,
is my thinking to teach also in a student in class. So start from the basics, go up to the higher.
yes, sir.
Okay, thank you, sir.
Okay, sir. Thank you,
Over to
sir. Thank you very much once again. I thank our today's session, Professor Dr. Jitendra Kumar Katiyar for sparing his valuable time and moreover presenting his valuable information, and I can say it's a knowledge shared to almost all participants might have enjoyed. The way he has presented various aspects of this tribology related to nanofluids and machining concepts and all, that was excellent. So once again, I would like to extend my heartfelt gratitudes to Dr. Jitendra Kumar Katiyar on behalf of the Department of Mechanical Engineering, Geetham School of Technology, Bangalore, and also behalf of the AICT Atal Academy. So this is our heartfelt gratitudes to you, sir. Jitendra sir, we always look forward to have you every time as a resource person, and more than such positions in the forthcoming events also. And I know like you have been giving support, joining as a resource persons in various aspects. So thank you very much, sir. Thank you all. And thank our participants also. Thank you.
Thank you, Director Geetham. Thank you, HOD, Department of Mechanical Engineering Geetham, and AICT Atal Academia to give me the chance. So thank you once again. Thank you, panelists, and thank you, attendees. Because of without them, nothing, no event will be successful. So at least after lunch, more than 70 participants and still here 63. That is a wonderful thing. So because I also always organizing so many events, I know what is the importance of attendees. I hope every attendees learn from this small presentation and understood, even though he's not in the same stream. So that is my thought. I just, with this thought, I always all the best for your future, and all the best to organizers for further 2 days this FDP, and hopefully we'll meet again in near future. So thank you very much to all. Have a good day.
Thank you, sir. Thank you very much, sir. Have a good day, sir. Thank you, sir. I thank all participants. Thanks for your active participation. So hope see you in tomorrow's morning session. So people are being very active on this chat box and all. Might have enjoyed this presentation from Katiyar sir. So hope you would be enjoying the forthcoming sessions also in the coming 3 days. Thank you all. Thank you very much. I'll be ending up now. Thank you.